and share screen. Okay, so this is the Hillgrove paper. Yeah, okay, so this is where we stopped. Does anyone need me to go through question 7? Can you just show by show of hands if you need me to go through question 7? Shreyans wants me to go through question 7, sure. Okay, just a note, right? If you do have any questions as I'm explaining, please don't hesitate to just unmute yourself and interrupt me. That's fine. Because I'm looking at 2 different screens here, so I can't always see your emoticons coming up, all right? So don't be afraid to just unmute yourself, interrupt me at any point in time. Okay, so let's go. Question 7. So this is a pulse generator connected to the clock of a decade counter. So this is the decade counter. So this is the pulse generator going in, all right? The counter needs to be reset after outputs 0, 1, 2, and 3 are displayed, and the cycle repeats itself. So 0, 1, 2, 3, 0, 1, 2, 3. Add to the diagram the connection for this to happen. Okay, so basically after 0, 1, 2, 3, I need these to be displayed, and on the 4th cycle, I need it to be reset. So this is the reset pin. So over here, I'm going to make a connection to the reset pin over here. Okay, so this will display 0, 1, 2, 3. But as it goes to 4, this signal will be input feedback into the reset. So it reset it back to 0 over here. Okay, so in this case, 5, 6, 7, 8, 9 will not have a chance to be displayed. It will only go 0, 1, 2, 3, reset, 0, 1, 2, 3, reset. Okay. So that is 7A. Okay, so complete the graphs of the outputs. Okay, so output 0, output 1, output 2, output 3. So this fella works on a falling edge. Okay, so if I'm not mistaken, this symbol means that it works on a falling edge. Okay, so every time there's a falling edge in a pulse generator, it will count up. Okay, so this is one falling edge here. So it will count. This is one falling edge. 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 So over here, it will count 0. Okay, it will count 0. So therefore, a 0 will go high here. All right. Now, the next falling edge is over here. So over here, next count would be a 1. So a 1 counts up. The next falling edge is over here. Then it will be a 2 over here. Next falling edge is over here. So next will be a 3. So the 3 will show a high or display, right? And then the next falling edge will come back to a 0 because the pattern is 0, 1, 2, 3, 0. Okay, so this, and then you complete over here, over here, just like so. Oops. So when you are drawing this on your own paper, please use a pencil and a ruler. Okay, you have to use a pencil and a ruler when you are drawing this. Yes, Shreyans.
Sir, after the last falling edge, there isn't any rising edge. So aren't we supposed to continue the output 0 instead of like making a rising and falling edge?
Okay, that's a good question. Yeah, I suppose you could do that. Yeah, so it'll stay. Yeah, correct. It should stay. It should stay as here. Yeah, correct.
Wait, sir, I have also another question.
Yes.
Why is it not 0 at the start? Is it just like null or?
Why is it not a 0 at the start? Is it, as in, why is it not here?
Yeah.
It will not be a 0 at the start actually, because if we assume that it's going to start counting 0 here, right? Then actually the start should be a 3. You get it? Because it's 0, 1, 2, 3, 0. So before a 0 appears again, right? It is a 3. But I'm just going to assume that this is when it the circuit powers on.
When the first falling edge occurs.
Yeah. So I'm just going to assume that this is when the circuit powers on. That's my assumption lah.
Okay.
Okay. Good questions all. Any others? I don't see any more hands raised. Okay. All right. So let's move on to this part. Explain what is meant by edge triggered input. Okay. So what this means is that the output goes high either at the rising or the falling edge. Okay, so basically what's that means? Okay, so the output, so what this means is the output will change when the input is either a rising or falling edge. Okay. So this takes the input at the time that the signal goes from high to low or vice versa. Okay, so basically keywords I need to see here. I need to see that it's either a rising or falling edge. Okay, the output changes when it experiences this. And what does rising and falling edge means? That it goes from high to low or vice versa. Okay. Okay, so next, a student wants to design a car when it counts when it counts the number of cars, complete the block diagram by adding connections. Okay, so first of all, you have to know that this is a LM301 voltage comparator. So it compares voltages. And what voltage does it compare? Well, first of all, I need to have a reference voltage. Okay, I need to have a reference voltage. So let's put the reference voltage into the inverting terminal. Now, some of you will be asking, hey, sir, how do I know whether the Vref goes into the inverting or the non-inverting? In this case, if you draw it, the Vref going into the non-inverting, technically it will still work depending on how you set up the sensor, right? Whether it is high to low or low to high, really depends on the sensor. If I'm not mistaken, you will still get marked correct. The problem is that it's not going to be as neat, okay, because these two lines will have to cross. So let's avoid that. Very simply, what we can do is do this. Okay, so the sensor goes into the non-inverting and the reference voltage goes into the inverting. Just keep it simple. Okay. Okay, next, we also need to be able to reset the count value. So there seems to be an input here. They did not specifically say what the input is, but if this input is taken and this input is taken, we only have to assume that this input is to reset the counter IC. Okay. State a suitable sensor. Now this one, a lot of you are using this in your coursework right now. So it's the IR plus photo diode pair. Okay. Does anyone have any other answer for this suitable sensor if you just want to check it out?
Sir, LDR.
Night dependent resistor. Yeah, possible. Any others? If Ray's was here, he'll say a PIR sensor, and that will also be possible. Any other possible answers you want checked out? Okay, if not, let's carry on. Okay, complete the table to show the 7-bit binary code needed to display 257. Okay. So 257. 6 has already been done. Wait, where's 7? Oh, sorry, 2 and 5 on a 7 segment. Okay. So 2, you have to know that 2 is here. Okay, so this is 2. All right. So knowing that, we need A, B, G, E, D. So you just write A, B, G, E, D. Okay, so we need those to light up. And this to not light up. All right. 6 is done for you. 5. Okay, so 5 is like this. A, F, G, C. Okay, so this is 5. So I need A, F, G, C, and D. Okay, and the rest will be 0. I think this is quite straightforward. Not much of an issue here. Okay, question 8. Sorry, before I go into question 8, any problems, any issues for question 7? Take that as a no. No one's raising your hands. Okay, if there are no issues, let's go on to question 8. Okay, so who needs me to go through question 8? Can you just indicate using an emoticon? Ashwin says no need. Okay, I don't see anyone raising their hands. I'll give you
Sir,
another
sorry, can we go through 8A?
8A, just 8A. Okay. Okay, so 8A, this BJT, this transistor is used as a switch, right? And we also have the option of using a mechanical switch if we want to, but obviously a BJT is better. Now, why? So there are a couple of reasons. The first reason is that it switches faster. So there is a faster switching speed in a transistor compared to a mechanical switch. Okay, so it switches faster. Second of all, and this is a big problem that a lot of you are facing now, is that a BJT does not have contact bounds. Yeah, so unlike a mechanical switch which has contact bounds, a BJT does not have. If some of you also would have thought that BJT does not also have wear and tear because there's no moving parts. Okay, so you just need to choose any of these two. Anyone here has any other answers that you want me to check? No? Okay, so we are good. We are good for question 8. Okay, we are good for question 8. Let's go on to question 9. Anyone needs help going through question 9? Please raise your hands. Ruhan, okay, I see you. All right, let's go through question 9 then. Okay. Okay, so a metronome is a device that produces a steady pulse to help musicians play. So a metronome plays beats from 35 to 250 beats. Can be built using a 555 IC. Okay, so complete the circuit of a metronome by adding R1.
So just part B.
Just part B. Okay, so the variable resistor R1 ranges from 0 to 150. Okay. Calculate the period T in seconds given that R1 is set to 94.2. Okay, so we are 94.2. Okay, so the period is, first you have to calculate the period. So the formula is R1 plus 2R2 C over 1.44. Okay. So first up, you have to know the formula. If I'm not mistaken, this is provided in the formula sheet on the front. Okay. So R1 is 94.2. 94.2 K. R2, which is here, is 1 K. The capacitance is 10 micro here. divide by 1.44. Okay, you press your calculator, you should end up with 0.668 seconds. Okay, so the key to solving this is, first of all, you need to know which formula to apply to find period of a 555 timer arranged in an astable configuration. Okay, Ruhan?
Thank you, sir.
Okay. Any other questions for 9? If not, if there are no questions, then what I'm going to do is I'm going to switch over to SST. Okay, the SST paper. Okay, can you all see the SST paper? Can I get like a thumbs up if you can see a SST paper, or a cross if you can't see? Okay, great. Okay, so this is the SST paper. I'm not sure whether you want me to go through like question by question, or do you want me to go through targeted questions? So I'm going to open the floor up to anyone who has any questions on a particular question. But if no one has any specific questions, then I'll just go through all the questions. So I'll give you all about 5 to 10 seconds to just shout out which questions you need me to go through specifically first. Okay. Once you know the question you need help with, just unmute yourself and just shout out the question number. Okay, no one seems to have any particular question. So what I'll do is that I'll just go through question by question, and along the way, of course, if you have any issues, don't be afraid to unmute yourself, ask, okay? Even if you need me to jump to a specific question that you suddenly realize I need help with, okay? All right, so now this SST paper, I looked through it. It is a very doable paper. It's probably not set by one of the lecturers that I know there. So it is of a doable standard, this SST paper, okay? So if you are able to do it, I think you are doing it, you are able to do it at O-level standard. If you find this easy, that's good for you. If you have issues doing this paper, then I would say that you need a little bit of bridging in order to hit the O-level standard. Okay, so let's start off with question number 1. Okay, state the voltage across capacitor C1. Okay, so over here, it looks like the capacitor is charging, and it's put, the switch is put in P1 for a long time. Okay, so keyword here, long time. All right, so if it's a long time, means it's got the opportunity and the time to fully charge itself. So some of you might be wondering, do I take the 5 tau, the 99.3%? So do I take 12 times 99.3% of that? Actually, no need. If it's a long time, right, you just put it as fully charged 12 volts. Okay, so don't worry about 5 tau and all that stuff. Okay, next, determine the charge stored in the capacitor. So you have to know this formula. The charge is CV. Okay, Q equals to CV, right? The capacitor value is 47 micro, and the voltage across it, as we saw in part A, is 12 volts. Okay, you press your calculator, you should get 560 C. Okay, C stands for Coulomb. Now, the switch is now connected to P2. So now the switch is here. So it's flicked to the other side. It is no longer over here. So now the switch is here. Okay. And with the switch over here, it means that now the capacitor is acting as the battery, and it is going to start discharging the charges accumulated. Okay. How long does it take for the capacitor to be fully discharged? This time to be fully discharged, the time is equivalent to 5 tau. Okay. And you know that 1 tau is equivalent to RC. Okay. And now knowing this, I know the value of R is 3.3 K. C is 47 micro. Press your calculator and you should get 780 milliseconds. All right. Now, some of you will be asking, is it okay if I leave my answer in seconds? Is that fine? Sure. Then is it okay if I change it to milliseconds? Also can. So this is possible. This is also possible. Okay. Estimate the voltage across the capacitor after discharging for 1 time constant. Okay. So after 1 time constant, after tau, okay, the V out will be 1/3 of VCC. So you got to know this, all right? The discharging is that after tau is 1/3, then fully discharged is 5 tau. Okay, so therefore, the V across will be 1/3 of the total, which is 12, which gives me 4 volts. Okay. Next, sketch and label the discharging curve. Okay, so first of all, you know that it starts at 12 volts. Okay, it starts at 12 volts, and then it will slowly discharge in this decreasing shape. All right, so 1/3 is roughly here. Okay, so I'm going to say this is my 4 volts. All right, this is my 4 volts, and this is my tau. Okay, this is my tau. And then once it reaches over here, this is my 5 tau. A 5 tau is 780 milliseconds. So tau is 780 divided by 5 is 156. So this will be 156 milliseconds. Okay. Any questions for question 1? Or is there a part F? Sorry, I think there's a part F. My bad. Okay, so these are the 3 positions X, Y, Z to place an additional resistor. Okay, so you can place one more here, you can place one more here, you can place one more here. Which positions will result in the described circuit outcomes? Increase the charging time only. So if I want to increase the charging time only, okay, if I just want to increase the discharge means I only want to talk about it discharging over here. Okay, I only want to talk about it discharging over here. So this is discharge. And if I'm talking about the circuit over here, this is where it is charging. Okay, so if we are only talking about discharging, I don't want another resistor here because this will affect both. I don't want this resistor here because it doesn't have anything to do with this circuit over here. So the only place that will have a connection to the discharge is at Z. So by placing it at Z, I'll only increase the discharge time. So like I was saying, position Y is going to affect both the discharge and the charging. So this is position Y. Okay. Okay, so that is question 1. Any doubts? Any other issues you have with question 1? Okay, if there are no questions, let's go on to question 2. Okay, so this is a potential divider circuit that uses a thermistor. The color of each band is brown, black, orange, gold. State the value of the resistance. I'm going to assume that no one here has any issues reading the resistance band of colors, okay? Anyone here needs help interpreting the colors of the resistance band? Please raise your hand or just unmute yourself. No? Okay, if not, the value is 10,000 ohms. And the tolerance gold, right? Gold is plus minus 5%. Okay, so that should be the answer you get. Okay, sketch on a graph the resistance of an NTC. NTC stands for a negative thermal coefficient. Okay, NTC. So what this means is that as the temperature rises, the resistance drops. Okay, it's a negative temperature coefficient. So this is how it will look like. As usual, please draw this with a pencil. Okay. Okay, describe and explain how the output Vout change when the temperature increase. So when the temperature increases, the resistance drops. Okay, so what's happening is that the resistance here is dropping. Okay, the resistance is dropping. And when the resistance of this drops, the voltage needed for the thermistor also drops. So therefore, the voltage also drops. Okay, so therefore Vout decreases. Okay. So when temperature increases, the Vout decreases. Okay. Now, why? Because you need to explain. Okay, Vout decreases. This happens as the resistance of thermistor decreases as temperature increases. Okay. All good? Okay, part D. Calculate the V out when the resistance of the thermistor measures 200K. So V out is over here. This is 200K. Wait, when the resistance of the thermistor is 200K. Okay. And this is, of course, 10K from what we found. Okay, so it's a very simple voltage divider method. V out is 200K over the total resistance, which is 200 plus 10. Okay, so just to run through again, some of you who are a bit confused about the voltage divider method, if I want to find what is the V out in between, I always take this resistor, because this is the resistor that will use out the voltage left, this resistor over the total, okay, to find V out, right? Times 6 volts, is 6 volts, right? Yeah, 6 volts times 6 volts. Press your calculator, and this should give you 5.7 volts. Okay. Okay, next, you need to have a Darlington pair. So complete the circuit to draw the Darlington pair. This one, actually, the good thing is that there's nothing to understand. You just need to remember how to draw the Darlington pair. Okay, so this one, even if you don't understand how a Darlington pair works, you can still get it correct simply by remembering the drawing for the Darlington pair. Okay, so of course, please use a pencil and a ruler. So the first step is, of course, I want to draw this one first. Okay, so I draw, don't forget the arrow. Okay, don't forget the arrow over here. And I'm going to draw a line down over here. Okay, so I'm going to circle this fella. Okay, and what's going to happen is that I'm going to draw, oops, I'm going to draw my first BJT here. Don't forget the arrow. Okay, and this fella will connect into the base of this fella. All right, and this fella will join the collector of this fella. Of course, draw the circle like so. Okay, so yeah, there's nothing really to understand about this. Just know how to draw a Darlington pair.
Sir,
Yes.
will we be penalized if we don't draw the circle?
To be honest, no. It's fine without a circle.
Okay, thank you.
Any other questions? Okay, if there are no questions, let's go on to question 3. Okay, so this is a practical diode. A knee voltage, VK or 0.7. What's meant by a knee voltage, and explain the significance of the knee voltage. Okay, so knee voltage, K is the voltage needed to turn on the diode. Okay, so that's knee voltage. It's basically a voltage, a minimum voltage needed to turn on the diode. And so what's the significance of the knee voltage when you are doing a circuit design? Basically, you must ensure in a circuit, the supply voltage must be greater than Vk for the diode to work. Okay. There are other answers as well, but this is it. So basically Vk is what is needed to turn on the diode, all right? And you have to keep in mind the consideration that the VCC must be greater than the Vk. Questions or alternative answers, please shout out. Seems like we are good. I don't see anyone with a raised hand. Okay, so let's move on. Okay, so this shows a circuit with connections AB. And this is a device that requires a correct polarity connection. So basically, I want the current to move from here. Oops. I want the current to move from the positive to the negative, okay, in a clockwise direction. So this fella needs to have this one at a positive polarity. If you don't, maybe it'll spoil, who knows, okay? So in order to make sure that the current only flows in this direction, what I can do is I can add a diode. So this is testing you, whether you know where is the anode and the cathode of the diode, okay? So you must know that this part is the anode and this part is the cathode. Arranged this way, it is forward bias and the current will only flow in a clockwise direction. Okay. This one should be quite simple. I'm not going to spend too much time on it. Let's go on to part C. Zener diode. Okay, so this Zener diode has the breakdown voltage of 6 volts. Okay, so basically it will want to hold the voltage at 6 volts. But if the voltage is below 6 volts, then the Zener diode is useless. Okay, so 6 volts, please keep it in mind. Okay, so R is 470. So let's write that down here. This is 470 ohms, and the load resistor is 500 ohm. Okay. Calculate VL. Calculate VL. Okay, so so some of you will be going, wait a minute, why is there a need to calculate? Because if this fella holds the voltage at 6 volts, there's really nothing to calculate. Because if this is 6 volts, then this one must be 6 volts, right? But not so fast, not so fast. I need to also consider whether the load resistance is high enough in order for the 6 volts to hold. Okay, so what I'm going to do is that I'm going to pretend that the Zener diode doesn't exist first. Okay, first. And I'm going to do a circuit analysis just based on R and RL. Okay, I'm going to ignore this value. So one good thing about this is that I can make things disappear. Okay, so I'm just going to make this value disappear for the time being. Like so. Okay, so I'm going to do a circuit analysis based just on this circuit. Okay, so I'm going to do again voltage divider. I want to see how much voltage this fella takes. So VL is RL over R plus RL times 9 volts. Okay, so RL is 500. This is 500 plus 470 multiplied by 9 volts. And this will give you an answer of 4.6 volts. Okay, and here we see that 4.6 volts is smaller. This is smaller than 6 volts, the breakdown voltage of the Zener diode. So if this is smaller, this is only 4.6 volts, it means that this Zener diode will not work. Okay, if you look back at the practical diode, so now this one is just a normal diode, but if this was my breakdown voltage, it will only work at 6 volts. It will only work at 6 volts. What we discovered just now is that VL is somewhere here, 4.6 volts. So if it's anywhere below the 6 volts, the Zener diode is not going to work. Okay, so that's what it means. So we can't assume that this answer is a straight up 6 volts. Okay. So now we have to say and explain if VL is regulated or not. So I just explained that it's not going to be. Okay, so you have to say that no, and why? Simply because VL as VL is less than VZ. Okay, therefore the Zener diode will not hold a voltage of 6 volts, and this is the VZ across it. Okay, okay. So summarize Zener diode. A Zener diode will only work. A Zener diode will only work if the voltage across the load resistor meets or is greater than the VZ. Okay. So that's essentially what this question is testing you on. Okay. Is there a part D? No. So that's the end of question 3. Any questions for question 3? I'll take that as a no. Okay, let's go on to question 4 then. Okay, so this is input This is a input and output waveform, V out 1 and V out 2. So we have two output waves of two different rectifier circuits. All right. Name the type of rectifier circuit. So this one, it rectifies the AC fully, right? Fully. So for every half wave, there is rectification. So this one is a full wave rectifier. So you got to write down that this fella is a full wave rectifier, right? Whereas this fella, you'll notice that half of the wave disappears. So it's only managed to rectify half of the wave. Therefore, it's just a half wave. Hey, why am I repeating half? Half wave rectifier. Okay, so number of diodes used in the circuit, you have to remember the circuit diagram. If you can't, this is where you need to look back in the textbook to revise. Okay, so a full wave rectifier uses 4 diodes, and a half wave just uses 1. Okay, between T1 and duration T1 and T2, how many diodes are actually conducting? Okay, over here, we're just talking about this time and this time. Okay, so over here, so you have to know that for a full wave, at any one point in time, at any half wave, at any half of the wave, only 2 diodes are working, are conducting. This is 2. Okay, so over here, 0 diodes are forward bias. Okay, the only so this is where the diode is in reverse bias, and that's why it's not conducting. Anyone confused? Raise your hand.
So could you explain for V out 2 again, the last part?
This one?
Yes.
Okay.
Thank you.
Now, conducting. Conducting. So you have to know that the let me draw this one. Okay. So this is my V out, right? So over here is when the current is conducting. Okay, so it's going, let's say for arguments, it's going in clockwise. Okay, so it's going in clockwise, and therefore over here, the diode is conducting because current is going through it. Okay, but now in the reverse cycle, so now the current wants to go over here. And now we are talking about this time, right? In the reverse cycle, the current wants to go in an anti-clockwise direction, but it cannot. It cannot, because now it finds that the diode is reverse bias. And if the diode is reverse bias, it means that it is not conducting current through it. There's no current being conducted through the diode here. So over at this point in time, no diode is conducting because there's no current going through it. In fact, it is stopping the current from going through it. Okay, Shreyans?
Okay, got it, sir. Thank you.
Any other questions? If not, let's move on. Okay, let's go on to question 5. Okay, so now we've reached the digital stage, yeah? Write the Boolean expression Q, R, and S in terms of A, B, C. Okay, so Q, let's start with Q. So Q is very simple. It is just the complement of A. So Q is the complement of A. Okay. R is OR. This is an OR gate. It's the OR of Q and B. Okay, but of course we don't write it as Q because we want it to write in terms of A, B, C. So R is A complement. Okay, this is A complement, or is a plus. Okay, so you have to remember or B. Okay, now let's look at S. So this one is A complement or B. Let's look at S. They did not say P, right? So that therefore we need to find out what P is for ourselves. This is a Nand gate. Nand gate. Okay. So what it does is that, so I'll just write P here. This is a B and C Nand. So this circle means that it is the complement. So it is the complement here. Okay. And this is another Nand. This is another Nand. All right. So this is another Nand. So I have B and C complement and A complement or B complement. Okay, so this is the N. And of course, I have a circle here, means I need to complement the whole thing like this. Okay. All good? Can Okay, so basically just work out gate by gate. So just take it one gate at a time. So you break it down, it's a bit simpler that way. Okay, so any logic system can be built using NAND and NOR gates. So such a gate is called a universal gate. You should know this. This one mark is yours for the taking. Please take it, right? So it is called a universal gate. Okay. Nand gate truth table. Okay, so Nand gate, this one, you either remember or you can work it out yourself, starting from an N. So N is 0, 0, 0, 1, and then a NAND, you just convert everything to the opposite. So it becomes 1, 1, 1, 0. Okay. Best if you can just remember it straight, makes it a lot simpler. This one mark also you can definitely get easily. All right. Okay, so substitute the logic gates in here, okay, using only NAND gate. So simplify the circuit to use as few NAND gates as possible. Well, so the good news is, of course, this is already a NAND gate. This is already a NAND gate. So now we just have to change this and this all into a NAND gate. So you just have to remember a NOT gate looks like this if I'm using a universal gate, all right? So I have one NAND gate Okay. Sorry. Why did I double it? Okay, so it just looks like this. Yeah. Whereas a OR gate, okay, OR gate is slightly more complicated, right? And OR gate is going to look like a flying V formation, right? So I have one NAND gate, I've got two NAND gate, and I've got three NAND gate. Look something like this. Okay, so we are going to use this and this substitute in here, right? And it should look like this. Okay. Again, this is going to look messy because I don't have a ruler. When you are doing it, please use a ruler. Okay. Okay. So I'm not going to simplify it yet. Okay. I'm just going to draw the whole thing out first. Then I'll simplify. Okay. So first was a knot, right? So a knot is simply this, and this was from A, I believe. This was from A. Okay. And then this goes into the OR gate, right? So the OR gate looks like this. So this is the OR gate, okay? Of course, this needs two input. And this one came from input B. So let's do a B here. Okay, so this comes from B. And this also B went into the NAND gate below with C. So this is, so this goes to C like this, okay? And then this and this goes into my final NAND gate over here. All right, so this is the equivalent of this. So basically what I've done is just replace this NOT gate and replace this OR gate, and these two stays the same. Okay. Now, now I'm going to simplify it. Okay. So now what I'm looking for are basically two NAND gates lined up front and back. So I spot this fella and this fella, NAND gate front and back. All right, so the NAND of a NAND is the original. So what I can do is I can cancel these two. All right, I'm going to use my eraser and cancel this. So this one, in fact, just comes into A. All right. And this then is my final simplified circuit. Okay. Any questions? Basically, to solve this problem, first of all, you need to be clear about the universal gate equivalent of a NOT and OR gate. So once you know that, then you again take it gate by gate, replace it gate by gate. And after that, to simplify, you just look at where do I have a NAND directly in front and back of each other. And those two, you can just strike it off. Okay. I'll wait for perhaps 5 seconds for anyone if you have any questions. Okay, looks like we are good to go on to the next question. Let's look at question 6, right? Okay, so battery powered lamp operates from 3 motion sensors. Okay, front gate, back gate, garage. The lamp is turned off if all 3 are off, or both the back gate and the garage are on. Okay, the lamp is turned off if 3 sensors are off, or both back gate and the garage are on. Okay, so basically, first let's look at this. If all 3 sensors are off. So I'm going to go with this first to fill this up. Okay, so if all 3 are off, so this is off, the lamp will be turned off, and that is the only time when all 3 are off. Now I'm going to look at both the back gate and garage are turned on. So I'm looking for back gate and garage are on. So I'm looking for 1 1. 1 1, there's a 1 1 here. So it's off. There's a 1 1 here. Okay, there's a 1 1 here. So it's off. Oh, the lamp is turned on in all other conditions. Okay, so I only have 3 possibilities where the lamp is off. Otherwise, the lamp is turned on over here. Okay. Write down the Boolean expression of L. Okay. So I've got 1, 2, 3, 4, 5. So I'm looking at 5 terms here because there are 5 situations where it is on. So I need 5 expressions. All right. So let's again tackle them one by one. Let's look at this situation. The lamp will turn on if there's A complement, B complement, and C. Okay. So A complement, B complement, and C. So first case, lamp is on, A complement, and B complement, and C. So this is done. Okay. Next, the second situation when lamp is turned on is A complement, B, C complement. So I get or A complement and B and C complement. Okay. Or there's a third situation, A, B complement, C complement. A and B complement and C complement. Okay, so this is done. Let's look at the fourth situation. Or there's a fourth situation. Or A, B complement, C. A and B complement and C. This is done. And now I go on to my fifth situation. A, B, and C complement. A and B and C complement. So this is done. Right? And this is how I come up with the Boolean expression. Just look at which output gives me a 1. And using this once, I look at each situation that will give me an output of 1. Okay. Next, I'm going to simplify this using K-maps. Okay, so let's populate the K-maps first. I remember someone asking me last week about how to populate K-maps, right? So very simple. I'm just going to populate the ones first, right? And then everything else will be 0. So these are the populations of ones, 0, 0, 1. Okay, so 0, 0, 1. So I look here. 0, 0, 1. So this is a 1. Okay, next, it is a 0, 1, 0. So I look for 0, 1, 0. So this is a 1. Next, I look for a 1, 0, 0. 1, 0, 0. Okay, 1, 0, 0 here. Next is a 101, 101, and the last one is a 111. Sorry, it's a 110. So this is 1, 1, 0. Okay, so so the rest, like I said, are zeros, and now we can start grouping them. So this one, unfortunately, doesn't give me a very nice group of 4 sort of thing, right? At most, we can group this one group, and we can group this another group, and we can group this another group. So all the ones are already grouped. Okay. Now, I kind of suspect that some of you would want to do this. Some of you would want to do this because you say, aha, the more groups, the better. And I can form one more group here and one more group here. Okay. But this is not right. Not because that these two cannot be grouped. You can group them. The problem is this fella has already been grouped here. This fella has already been grouped here. So if you group them again, you are kind of double grouping them, and you're creating an unnecessary group. Okay, so you're actually complicating things for yourself. So I don't want this because these two have already been grouped. Okay. I also suspect some of you would want to group one big group here, right? One big group here. Okay, because you say, Mr. Yo told me the bigger the group, the better, right? However, this is also wrong because I also told you that groups must be groups in 1s, 2s, or 4s. Okay, you do not group in terms of 3. So this is also wrong. Okay. So these are my 3 groups. Okay. Okay, so from here, actually it's a good thing. It's better than nothing. Originally we had 1, 2, 3, 4, 5 groups. But now we are going to end up with only 3 groups, right? Because I got 3 circles. So it's still a simplification. We are cutting down from 5 groups to 3 groups. So it's still good. So let's take a look here. Let's look at this group first. Okay, let's call this group 1. Okay. So in group 1, I'm looking for things that don't change, and that's what I want. So if I move from here to here, A doesn't change, which is good. I want A. Okay. And from here to here, right? 0 doesn't change. So I want B. I want B. C changes from 0 to 1 as it shifts from this box to this box, right? 0 to 1. So I do not want C. I want B. But since it is the B of 0 that stays, so I want the complement of B. Okay? So now I'm going to go on to this group 2. This group 2 here. A changes, right? It moves from A0 to A1 as I go from this box to this box. So I don't want A. Okay. B and C does not change, right? It stays as 0, 1 over this box. It is still 0, 1 for B and C. So B and C I want. So or B complement because it's the 0 of the B that we want, and C1. Okay, now let's look over here. I have my third group, or A changes from this box to this box. A changes from 0 to 1. So I don't want the one that changed. B and C stays, right? From here, B and C is 1, 0. Move over here, B and C is still 1, 0. So I do want B and C complement because C is 0. Okay, and there we have it, our Boolean expression, simplified Boolean expression. Okay, and over here. So they need us to draw the circuit diagram using this Boolean expression. So same thing, let's do this one group at a time, right? So let's settle this group, A and B complement. So this is A and this is B. So what I'm going to do is that I'm going to have a NOT gate here. Okay, because this is going to give me my B complement. So the first group is an AND gate. AND gate. Here, this is my A, and B complement. Okay, so this is my A and B complement. All right, so let's look at my second group now, B complement and C. So this is my second N. So I can just take this. This is my B complement and C. This is and C over here. Okay, so this is my B complement and C. And lastly, let's go on to my third group, B and C complement. Okay, so from here, I need a C complement. So this gives me my C complement. I also need a B, right? So I need to draw before the NOT gate a B. So let's draw this into our third AND gate over here. So this is my B and C complement, right? And all of this will enter into one OR gate. So my OR gate will be a 3-input OR gate. So this is my first input. This is my second input. And this is my third input. Okay. Any issues? So remember, draw using a pencil and a ruler. Make it as neat as possible. Make sure all your lines are horizontal or vertical, no diagonal lines. Okay, I'll wait 5 seconds for any question.
So for question B, I had a issue.
Question what?
B, part B.
Yes, what's the issue?
Before you said that we can't group ones like 2 times. Then but then isn't there one that has been grouped 2 times already?
Oh, this fella.
Yeah.
This fella. Okay. So in order to group this one guy, I need, okay, so I have the option. Of just grouping one, correct?
Yes.
But I told you that the bigger the group, the better it is. So instead of just grouping 1, I prefer a group of 2. Now then you'll be saying, hey, but sir, you just told me that try not to group the one that has already been grouped, which is this. Now in this case, no choice, because in order to form a group of 2, I need to use the factor where it's already been grouped. What I'm saying is that over here, all the ones are already grouped. There is no one that is ungrouped. Okay, so my job here is done. I do not need to group any more ones. So if I'm saying, if you still want to group this fella and this fella, this is unnecessary because this fella is already grouped. This fella is already grouped. There's no more ungrouped ones. Whereas over here, this situation, I have one ungrouped fella. I need to group him. I cannot leave this one guy ungrouped. Okay, so this case, no choice. I have to use this one fella who is already grouped, and this is fine. What I'm saying is that over here, there's no more need to group because all the ones are already grouped. Okay, if you still insist on grouping this fella and this fella, you're going to create another term, which complicates matters actually. So I hope I've explained that satisfactorily.
Okay, got it, sir. Thank you.
Yeah. Okay, so yes.
What if you only group the single one with the one on the other side of the K-map? Like you only do that.
You are talking about this one, is it? Like that.
Yeah.
Oh, that's fine also. This is another way to group as well.
Oh,
So this is
okay.
also fine. Yeah.
Thanks, sir.
Yeah. Any other questions? We are good. Okay, if not, unfortunately, the time now is 1 o'clock. I realize that you all need to pack up, have your lunch, and then come to school to see me at 2 o'clock. So I'm going to end the lesson here. I'll put up the recording on YouTube later today, and I will also post the answers to our WhatsApp group. Okay, but again, if you have any questions later on when you come for class, you can still ask me face to face. All right. Any last questions before I end the session?
Nope.
All right, cool.
Yep.
Okay, so I will stop the recording now, and I will see you guys later at 2 o'clock. All right.
Okay.
Okay, see you.
Bye, sir.
Bye. See you.
Thank you, sir. Bye-bye.
Okay, see you later.